Okay, I want us to start the session. Good afternoon, everyone. Yes, I'll be your moderator for this afternoon. I'm Joski Kisali. I'm a geologist. I work for the Ministry of Energy and Petroleum, Kenya. And I've been working in the ministry since the year 2010 up to now. So we are going to start our session. We are looking at best practice exploration in sedimentary basins. I remember this session started yesterday, later on in the evening. And also we've had country presentations whereby each partner state was presented on the exploration potential and the basins. So there is slight change of plan. First of all, I need to know if my presenters are around before I inform you of the slight change in plan. Asenet, I know you are around. Jen, I've seen you are around. That's Jen Oremo. Asenet Kwagalake, you are around. Wangese Misiwa, are you around? Wangese Misiwa? Dr. Olumiyiwa Olowaki. Is he around? Mr. Venance Emmanuel Lazaro Mboya. Thank you. So we have 3 presenters around. So the change of plan is that we have a presenter who was supposed to present in the next preceding session, East African Offshore Coast and Rift Basin, called Ms. Suganda Tewari. Since she has a flight, so there was a request that she moves to this session. So we are going to start, because I think the topic is the same, whether you are talking about coast or the old sedimentary basins, and we want to learn the practice. So the plan is that we are going to start with Ms. Suganda Tewari. She has 17 years experience in oil and gas industry, and currently she's working as exploration lead for Africa and Europe. That is for Slambaj. Karibu sana, Suzanne. Thank you.
Good morning, good afternoon, everyone. And I would like to thank the organizing committee, first of all, to give me the opportunity to present here. And I would also like to thank the committee for, understanding the situation and being flexible and giving me the opportunity to talk now. So then that is really appreciated. All right, so I'll start with my talk, which is in a very interesting basin, which is the Pemba Zanzibar sub-basin. We are going to talk about some findings from the Pemba and Zanzibar Island and how we relate it to the offshore underexplored areas of Pemba and Zanzibar to the unexplored area offshore Pemba and Zanzibar Island. So as you can see, there is a list of authors here. So we have been collaborating with academia. We've been collaborating with ZPRA on this project. So it's a collaborative project where we've imbibed the learnings and understanding from each and every organization. Right, so you can move to the next slide. Yeah. Right, so in this map, you can see the exploration activities that are happening on the East African margin. When I start this presentation, I'll talk about the Pemba and Zanzibar Islands. So there was very, very sporadic and intermittent activities that happened in Pemba and Zanzibar. And the activities, when we talk about the wells drilled, We have Pemba 1 all the way up to Pemba 5 well that was drilled back in the 56 to 61. That was the time when there was exploration activity in Pemba and Zanzibar. Zanzibar 1 was 61, drilled in 1961, and Zanzibar 5 well was drilled in 1956. So in terms of what are the findings from these wells, they're very interesting wells, 2 of them, although they were not commercial, but they gave a very good sense of understanding about the working petroleum systems, because they had hydrocarbon shows, and they had both gas shows, and also it was, dead oil was encountered, which again, even if it is not commercially viable, for explorers it is quite important information, because that is something we can build onto and translate to the unexplored areas, because it helps us to understand about the petroleum system. It is giving us an idea about the maturity of the source rock. So again, a very vital piece of information for us. Now again, when we look into what is happening in the southern part or in Tanzania, we see a lot of discoveries. Mainly there was a ramp up of activities in the early 2000s. So we see a lot of gas fields that were discovered. And again, abundance of gas presence in the margin as whole. Looking into Lamu Basin in Kenya, we're looking at oil discovery, that is Sunbird 1 oil discovery that probably you're aware of. And then, we've got gas discoveries as well. So what does it tell us? It tells us that there is a working petroleum system. There are elements in place, and it is about the time that we start exploring the unexplored areas and venture out into the deep water. And the deep water trend is now becoming quite an established trend, especially even if we take the learnings from the west coast of India, west coast of Africa. We've got, 2 large discoveries in 2022, Venus and Graph. So again, these were deep water turbidite fans. So again, learning, if we take those analogs and apply it here, it gives us the confidence in saying that we do see a lot of prospectivity even in the deep water areas. We see the Oligocene reservoirs, the Eocene reservoirs. We see incised channel systems and basin floor fans all the way from Cretaceous to the Tertiary. So again, we have all the elements that we can find just to confirm that the basin is productive, and we feel that it is a productive basin. And we'll see as we move into the next slide all the studies that we've done, which will give us a confidence and assurance in saying that it is definitely a very prospective area. So here we've got the tectonostratigraphy, and we're looking at the pre-rift, which is mainly the Carboniferous to early Jurassic, continental deposits, Karoo deposits. That's the pre-rift phase. Gondwana rifting, when we refer to that, starts in the late Jurassic, all the way it goes up to the early Cretaceous, that is the Synrift phase. And then during that time, we have the development of these lakes, and that is where we have development or deposition of lacustrine source rock, and we have fluvial conditions in the beginning, and then we transition from the lacustrine to more of a fluvial deltic environment when we have the fluvio-deltic reservoirs present. So again, we've got the lacustrine source rock, we've got restricted marine source rock, we've got the fluvial and deltic reservoirs during the Synrift phase. As we progress into the ref development, we enter into the open marine condition, that is the formation of the passive margin, where we have formation of deltas on the coast, and then we have the progradation of these deltas in the deep water with time and with either it could be gravitational effect, or either there could be some sort of tectonic activity which is resulting in gliding down of the sediments into the deep water, forming the famous turbidite sequence that we know of. So again, when we are in the open marine conditions, we are mainly relying on the marine source rock type 2, that is what, and the reservoirs, again, very good quality turbiditic reservoirs. Right, so if we move to the next slide, please. Yeah, so in this slide, we'll talk about the petroleum systems. Before we do that, I just want to highlight that for this study, we used 2D seismic data. Also, we refer to a lot of analog studies done in the margin. We also took advantage of 2D lines which we got on the Pemba Zanzibar island and tracking it back to the coastal area, getting a regional context into what is happening in the Pemba Trough area and moving out into the Pemba Island and how that translates down in the deep water area. So what we see are numerous petroleum systems or numerous play types all the way from the Jurassic tilted fault blocks moving into the Cretaceous basin floor fans. As we progress in the upper Cretaceous, we again witness a lot of these basin floor fans which are pinching in up-dip direction, forming a very good stratigraphic trap, and then moving on to the Tertiary where we see a lot of incision and channel systems, incised channel systems being developed. In terms of the source rock, we are relying on the Jurassic, mid to late Jurassic source rock. We are also relying on the Cretaceous source rock, that is Neocomian and Campanian, and we are looking at, also we tried to model the Eocene source rock, and we will see some of the very exciting results in the next slide. So this is a slide which is showing the petroleum modeling exercise that we've done. And on top, you've got the facies assignment, and I can just read out the colors if you can't see the legend. So the buff color or the brownish color that you see, in the background is mainly shale. The yellow color is sand. The light yellow color is the silt, and the red color that you see over here, deep red, is the source rock intervals. And then we've got the pink color, which you see on the, where we've marked volcanics. So we've seen some intrusives within the area. We've seen a presence of dikes and silts. And in terms of modeling exercise, what we've done, we've realized that, contrary to the thought that the presence of volcanics is bad, here what we've witnessed is in some areas we've got these volcanics, but they have a very isolated or a very, not a very global effect, but they have a very localized effect. So they might be heating up the source rock in the vicinity, but they don't have they're not over maturing the source rock everywhere. So in the next seismic, sorry, can we go back to the, yeah. So in the next image that you have below, where you see the transformation ratio, that is showing us the maturity of the source rocks. So what it means, if we have 50% transformation, that is conversion of organic matter to hydrocarbon, we say that we are in the critical moment. Anything above 15, if we reach 15% of transformation ratio, we say that it is, the expulsion has begun from the organofacies. What we are looking at here is transformation ratios telling us when we're looking at the deeper source rock, we've got 100% transformation of the organic matter into hydrocarbons. When we're looking at the Eocene interval, it's very interesting because in the Pemba Trough area, where we've got a subsequent overburden, we see that the transformation is happening even even for the Eocene source rock, which is a very promising thing because we've seen, oil presence in Lamu Basin, and we can correlate to the fact that, we are not in a very, under a very thick buried sediment overburden, but we are just in the right place that we might have some oil, and we've seen some long distance migration. So it is a good news that especially in the Pemba Trough area, when we're looking at it, we are seeing a very positive story, and that is also complementing what we might find in the deep water. So again, gas, yes, and oil, definitely. There is scope of, some oil presence as well. So the next slide is highlighting the petroleum systems events chart. So what it means, it's placing all the elements of the petroleum systems like the source, reservoir, seal, overburden in place. And so in order for a petroleum system to work effectively and for the source rock to expel and accumulate hydrocarbon, all the processes plus these petroleum systems elements should be correctly placed in space and time. Now, when we're looking at the picture on top, that is from an area which is closer to the coast, And the one below is in the deep water, where the water depth starts from, let's say, 500 all the way up to 3,000 meters. So when we're looking at the top picture, what we are seeing over here is that the critical moment, if we look at the Jurassic petroleum systems, considering we have got a carbonate buildup or we've got the clastic Jurassic reservoir, and if we have a source rock deposited during the mid-Jurassic and we have the seal on top of it, the critical moment is happening around the early Cretaceous, which means before the generation starts, we've got all the elements in place. So whatever has been generated is contained within that petroleum system. So everything that was generated in Cretaceous is already contained or accumulated in the Jurassic reservoir. Then when we look at the next source rock, which is the Campanian, again we look at all the other elements like the source and the reservoir and the overburden or seal in place. If we look at the critical moment, it is happening around the mid-Cretaceous. That means that we still have some lower Cretaceous plays which are probably being, or the reservoirs being charged by the Campanian source rock, by the Neocomian source rock. When we look at the Campanian source rock, then we have all the other underlying petroleum systems. Even when we speak about the lower Cretaceous play type, or we talk about the Campanian play type, we would have accumulation coming in from the Campanian source rock. And what is very interesting here is to note in the picture on top is that we've got the expulsion also happening from the Eocene, because Eocene has also started generation, right? And when that is happening, if we've got, if we are in a trough area, as we move into the high, we would have some underlying, reservoirs which are probably deeper or they're older. They would be also charged by the Eocene source rock. So again, it is giving a very promising evidence that we've got all the elements that are needed for working petroleum systems in the Pemba Zanzibar island itself, in the sub-basin, and also as we move out into the deep water. The story is more or less similar. So again, very promising outcomes from the study. And in the next slide, I will conclude the finding or the essence of. So we've seen that there are established or proven source rock along the East African margin, and especially when we talk about the source rocks, it's more of a regional phenomena. They deposit over the larger interval. So again, we have very promising. We have presence of established and proven source rock. We have numerous play types. We've seen Jurassic all the way up to Tertiary. Jurassics, we could also be, thinking of carbonate build-ups over these rifted fault blocks. They could be clastic reservoirs as well. And then we are looking at the Cretaceous basin floor fan, the Cretaceous turbidite sequence, lower Cretaceous and upper Cretaceous. And as we move into the Tertiary, we start seeing development of very nice incised channels and, which are again very promising reservoir potential. So in terms of activity-wise, we've seen that exploration in the Pemba Zanzibar and in the surrounding areas has been very sporadic and intermittent. There hasn't been enough efforts in terms of exploration activities. However, with the study, we have seen that it does look like a promising area to work. So again, it has a lot of potential, a very promising potential to be explored. So with that, I would conclude. Before I conclude, I want to acknowledge Zanzibar Petroleum Regulatory Authority, ZPRA, and all of my co-authors who've contributed for this paper. And thank you very much.
Thank you very much, Suganda, for your wonderful presentation on Pemba Zanzibar trough. You've indicated that the trough has potential, and we know the trough moves all the way from Mozambique to Somalia. So there is high potential there, and we encourage investors to come. So if you have any question, you just note it down. We'll do it at the end. I promise that we will be very quick so that you are able to catch with your flight. Let us appreciate her again. So our next presenter is Asenath Kwagalake. She's going to present on investigating melt generation beneath the northwestern branch of East Africa using 3D geodynamic modeling with aspects. Asenath is currently a PhD student at Virginia Technical Institute, pursuing PhD in geophysics. She has a master's and a bachelor's degree in geology from Makerere University. Please help me to welcome Asenath.
Hi everyone. Hi everyone, my name is Asenath Kwagalake. I am a third year PhD student at Virginia Tech in the US doing geophysics, and today I'll be presenting to you part of my project on investigating melt generation beneath the northern western branch of the East African Rift using 3D geodynamic modeling with aspect. So as a geophysicist, I'm happy to share with you how we can use geodynamic models or computer models to simulate what happens beneath the crust. So on the upper left figure, it's a cover page of the aspect manual. So aspect is a code that I'm using to do my geodynamic models. It's an open source code, and aspect is an acronym that stands for Advanced Solver for Problems in Earth Convection. So in case you want to know more about, you can find it online, but also here I'm going to explain what exactly it does. And then the lower figure is a photo that we took in that area indicated by the star. So that's part of the northern western branch, and the map shows the extent of the northern western branch. So first and foremost, I would love to acknowledge all my funders, the US National Science Foundation, and all the funders of this conference who took care of my travel expenses, CIG that provides the code that I'm using, and all my collaborators listed here from various institutions. So much as I'm standing here, but there are lots of people who are behind this project, and probably some of them may be in this room. So as an overview, I'll give a brief introduction of the northern western branch together with our motivation, and then I will talk about the aspect code that I use with other supporting models. I will discuss my results, and then later, finally, I'll conclude. So it's important for us to understand continental rifts because they represent the initial stages of a continental breakup. As all of you may be knowing that they host precious metals, petroleum, but on other flip of the side, they could cause emit gases like carbon dioxide and methane that could affect climate change. Sorry. I'm sorry. I think I must have skipped. Okay. So let me do this slide. So first and foremost, the motivation of this study is for us to understand the tectonic forces that are affecting or that are enabling the continental rifts to occur beneath this particular part of the rift. And I am going to explain to you how this is connecting to the audience here with the petroleum. And then our main objective is to determine whether there is melt. So for the non-geoscientists in the room, melt is simply a rock that is melting. So I'm going to use that word a lot, melt or magma. And then our specific objective is to model melt generation and lithospheric moderated convection. So back to this slide. So basically, the processes or the forces that could cause the lithosphere to stretch, and one of it is the mantle traction or far-field forces. However, several authors have indicated that these forces are insufficient to overcome the strength of the lithosphere. And here what we are calling tectonic force paradox. So basically when a rift is occurring, there are things that could help, or what we call like, that could trigger the rift to keep rupturing. And one of it is melt. We have pre-existing structures or fluids. So rifts can be magma-rich, and this means that there's evidence of magmatism, like volcanoes, hot springs, or they could be magma poor where there is no any evidence of magmatism. So the map you see on the right, it indicates the extent of the eastern branch and the western branch of the East African Rift, and our study area is indicated by that blue box. So zooming into our study area, the northern western branch has two segments. It has the magma poor region, which is basically the Albertine and the Rhino Graben, and it also has the magma rich region, which is the Lakes George Edward Graben. And in the Lakes George Edward Graben, the volcanoes in this area are known as the Toro Ankole volcanic province. So this kind of rift is an asymmetric fault graben, and it's said to terminate along the Astra shear zone. So the number of earthquakes that have been observed in this region that range from magnitude 3 to magnitude 5.9. So what's our research question? So we are looking at what is the weakening mechanism enabling this rift to rupture, and we make two hypotheses. So in the magma-rich region, which is the Lakes George Edward, we are hypothesizing that probably there is melt underneath that is kind of helping this rift to occur. And also in the magma poor region, that's the Albertine and Rhino Graben, we are hypothesizing that probably melt is underneath but hasn't just bleached the surface. So overall melt is helping for this kind of rift to rupture. So the aspect code that I've been talking about. So this is a geodynamic code. So for those of you who may not be knowing, a code is just simply a bunch of numbers, a bunch of math. So here we solve quite a number of equations, physics that we do. So we solve the conservation of mass, the Stokes equation, and then the energy equation. And this kind of code does a lot of things, but in this particular project, we use it to model or simulate melt generation and lithospheric moderated convection. So lithospheric moderated convection is just mantle convection generated from temperature differences that are caused from lithospheric thickness. So, and that simply means that in an area where when the thickness is thin, when the lithospheric thickness is thin, you expect upwelling, and where the lithospheric thickness is thick, we expect downwelling. So in the code, we also do quite a number of things. I might just run through them, but in case you are interested, I'll stick around after this talk. So we solve nonlinear rheology, bunch melting, chuck geometry. Our model is time dependent, so we model for 20 million years, and then we set initial conditions. So still this slide is just showing the physics that we solve. So it's a bunch of numbers and a bunch of parameters that we put into the code. But it's a lot here that I won't go through, but you can still reach me out after here, and then I can explain more. So this slide explains an example of the setup model. So as you can see, that's like the visualization that we use like in another software called ParaView. So this just shows you can be able to see the crust, the mantle lithosphere, the sublithospheric mantle, and then we set initial conditions like temperature, density, and viscosity. So yes, so this slide explains in our code, the code is constrained by the thickness of the lithosphere. So we have this assumption, and where the lithospheric thickness is thin, we expect melt to be there. So in our code, we have to put lithospheric thickness files, but here we use 3 lithospheric thickness models that are based on seismic observations. So we have Fishwick model, we have the Litho 0.1, or we have the Alfonso model, which is the recent one, which was published last year. So why are we using the three? Because we want to weigh all the parameters to see if exactly is there a melt underneath this area of our study. So moving on to the results. So in general, in total, we carry out 39 experiments using based on those three lithospheric thickness models. And then we also, our model is constrained by the temperature. So we run mantle potential temperatures ranging from 1,643 Kelvin to 1,763 Kelvin. And the figure here you're seeing, or the table here they're seeing, it's kind of not so clear, but the highlighted one is showing the areas where we're seeing melt. And the region where we're seeing melt is the area which is the magma-rich area, the Lakes George Edward down here, that's where we're seeing melt. But we don't see any melt in the Albertine, we don't see any melt in the Rhino Graben. And that's according to the Litho 0.1 or lithospheric thickness map. So still, this is for Fishwick. We don't see any melt in that region. And then also for come on. Next slide, please. Okay. And then for the Alfonso, still we don't see any melt. So this slide, it just explains the visualization of everything. So it's the same map that I was showing, but here we are able to see exactly where the melt is. So we see the melt in the Lakes George Edward Graben down, and also up north in South Sudan, we see melt. So it's just part of explaining, and the mantle and the melt fractions are also indicated in the scale below. So finally, why is this important? Why is this important to you people? So as I've mentioned, we're not seeing any melt in the magma pore region, in the Albertine and Rhino Graben, but we see melt in the Lakes George Edward, which is down in the region. And most of you may be knowing that the melt or the heat is so important for petroleum generation. So we are able to constrain, in our results are able to help us constrain the sources of heat and melt generation in this particular rift. And our next project, or which I'm currently working on, is to investigate pre-existing structures using still the same code aspect. Thank you so much. I don't know how I'm doing with time, but in case of any questions, please don't hesitate to reach out to me.
Thank you, Asenat. I think you presented a model that is investigating melt generation beneath the surface. And I think also the tool can also help in geothermal, if I'm not wrong. It's a good tool that all of us can appreciate, and also it can also be used to, demarcate where the zones are. Let us appreciate her for the last time. So our next presenter is Venance Emmanuel Lazaro Mboya on geology of EAPCE Wambere Frontier Basin Potential for Petroleum Exploration and Exploitation, a promising investment opportunity in Tanzania. Just a small background. Venance Emmanuel has been working as a petroleum geologist at Tanzania Petroleum Development Corporation, that is TPDC, and before joining, he worked at a Geita gold mine as an exploration geologist. He holds an MSc in structural geology with geophysics from the University of Leeds in the UK, and also as a master's in geology and a PhD geology from the University of Dar es Salaam. Venance is also a member of European Association of Geoscientists and Engineers. Allow me to welcome Venance. Karibu sana.
Good afternoon. Yeah, welcome to my presentation. is all about East African Rift. Yeah, in a part of Tanzania, the eastern arm of East African Rift. The title is on geology of Ayers Wembere. It's a frontier basin, but potential for petroleum exploration and exploitation is a promising opportunity for an investment. Yes. Yeah, in my presentation, I'm gonna talk about, I will introduce about our basin, then a little bit on regional geology and the local geology. I will show you the information, all the works that we have done so far. And I will highlight you on way forward, what do we do anticipate or planning to accomplish as a way forward. And I will give you some conclusive remarks. Yeah, our basin is located in the northern eastern part of Tanzania, and it is within the eastern part of the East African Rift. Yes. All right. It covers an area of about 19,197 kilometers, extending from the Natron to Ayers and Wembere southward. And within, there are some number of sub-basins which are disconnected by some structures. However, the study is much, or the activities are much concentrated in the southern part of this this basin or block, simply because the northern part is more affected by volcanic activities. Looking at the regional and the local geology of this basin, as far as we know that our basin is within the East African Rift, and this rift, the East African Rift starts from Arafa Triple Junction all the way down to Mozambique, before dividing to the western part and the eastern part or eastern arm of the East African Rift. Its evolution, when we look at our part, we see that it started, the deformation started since Miocene by first faulting, and during this period is the time when it triggers some erosions and depositing some clastic sediments, and these are the conglomerates, sandstones, and some clays or shells. Then later, during Pliocene, the deformations again triggered the volcanic activities, and these volcanics affected the northern part of this block with the number of volcanic arcs and some basalt flows. And later, during the Quaternary period, and this is during the late Pliocene to Pleistocene, with the second faulting event, and this again, this again was shifted to the eastern ward with the formation of the current big Gregor Rift, and this is the the eastern rift arm. And with the time now to Holocene is where now we have a lot of deposits of lake beds. Now looking at the geological map, we generated a geological map of this area, and we saw about 3 packages which are conforming to the major tectonic events. And this marks the, shows that the Miocene deposits were the clastic sediments, followed by the volcaniclastics during volcanic eruptions, and later the lake beds on top. Then we did AGG, that is airborne gravity gradiometry, just to understand the subsurface information, basically the structures and the configuration of this basin. And it demonstrated to have a sufficient thickness of sediments and potential structures good for migration and a trapping for the any hydrocarbons that can be encountered. Yes, and again we did some drilling of some boreholes because our area is too flat, very few outcrops. So these short boreholes were to aid understanding of the stratigraphy. They are about 300 meters. They range from 170 to 300 meters. But we couldn't achieve intersecting all the 3 sediment packages. We only intersected the upper part, which is Holocene, and some of the volcaniclastics. Then with these boreholes, we did some geochemical analysis, biostratigraphic and petrographic analysis. And we are anticipating to perform geological dating of these sediments so that we constrain better the geological history of this basin. Geochemically, it is indicated that we have type 2 and type 3 kerogen, potentially for oil to gas, or gas to oil, petroleum oil or gas. Then we did some modeling as well, where we have a 3D model of the basin, depicting some compartments of the basin, and remote sensing as well, just to understand the presence of seepages. And we managed to get some few points of leaks, gas leaks. And with this information, we did again AGG. Yes, AGG amplified geochemical imaging with the aim of capturing any seepages within the basin. And the good thing was there was a good, each information complement the other one. We did some petrograph for the volcaniclastics, just to understand the varieties of volcaniclastic sediments, but also we were looking for the presence of the detrital zircons, but we didn't manage to get it for geological dating. Looking at the way forward, we are finalizing interpretation of the AGG, which is good information for areas of concentrations and to aid us to replan the 2D. We anticipate to do 2D seismic data acquisition. So with this information that we have, they're gonna give us a very good planning for 2D seismic. Then concluding is that the information we have, we can see that they're complementing each other and they're giving us some confidence for what we are doing. And looking at the block, we see like it is within the strategic area where we have even the eco pipeline cross near the block. And this is good for commercialization purposes when we have discovered oil in our part. So TPDC is inviting potential investors to collaborate with, because we are heading into very high level of explorations. Then we need to collaborate with any investor who is wishing to unlock this potential which is available in our basin. Thank you.
Thank you very much, Venus Emmanuel. As you know, in Tanzania, we have resources, discovered resources offshore. But now I can see very nice potential onshore. And looking at the landmass, I think East Africa should be having huge resources. We're just waiting for that moment. Thank you very much. So we are going to our next presenter, who is Jane Oremo, on geochemistry of rocks, groundwater, and sediments. That is in block L16, Kenya. Jane is a geochemist at the Ministry of Energy and Petroleum, Kenya. She holds a Bachelor of Science degree in chemistry and Masters in chemistry from Masinde Muliro University of Science and Technology. She has presented in various conferences, including laws and policies for chemical management systems towards responsible consumption and production in Kenya, amongst others. She has worked as a laboratory technician and an analyst. Karibu sana, Jen. Let us appreciate her as she comes. Maybe I want to know if Olumiyo has come. Olumiyo, has he come? No. Wangese? No. Okay, proceed. Thank you.
Good afternoon, everyone. I'm Jane Oremo, a geochemist, and I'll be giving a presentation on the geochemistry of rocks and sediment in block L16, Lamu Basin. Okay, my main focus will be on surface geochemistry. And surface geochemistry is a tool that is used to detect, to record and analyze trace amount of hydrocarbon in rocks, soil, and sediment. So for general objective, we are going to determine the geochemistry of rocks and sediment in block L16, Lamu Basin. And to achieve that, we divided our objective into two. The first one being to determine the trace metal content in rocks and sediment, and to determine the total organic carbon in rocks within zone 1, Lamu Basin, Kenya. Okay, why we needed to do the study was to look for the potentiality of hydrocarbon in zone 1, Lamu Basin. And also geochemistry is a tool that is very effective. Okay, why we needed to do the study was to find the potentiality of hydrocarbon in Lamu Basin, Block L16. And also geochemistry is a tool that improves the effectiveness of hydrocarbon exploration by de-risking exploration activity. Okay, the map shown there is the map of the block L16. And for us to carry out a detailed geochemistry, we decided to divide it into 5 accessible sections. As you can see, it's on onshore and offshore. So our focus mainly is on zone 1, which is the upper part. And those are the latitude and longitude of the zone 1 for the 4 corners. Now moving on to methodology. For objective 1, which was for the trace metal element concentration, we did the sampling of the surface outcrop and the road cuttings, and did the sample pretreatment. Then the sample were analyzed in the laboratory, and we did using the XRF. For TOC analysis, we did the sampling method was the same as the objective 1. Then we did pre-treatment. We did analysis using TOC analyzer. Under results, for trace metal concentration, as you can see, I don't know if it's clear enough, but for figure 1, under our, one of the sampling site, you can see the concentration of silicon oxide was the highest. And this implies that, the presence of sandstone, which is a very good source rock. For the other 2 figures, you can see the concentration for calcium oxide was the highest, which imply limestone, which is also a very good source rock, and which is a carbonate rock. Still on results, this was now for the trace element now in sediments. The other ones were the rocks. We used Sulfur9 software, and you can see for the concentration of copper, the first figure, the threshold for copper is 0.03%, and you can see the blue part, the lower part, had a concentration lower than the threshold, which is 0.003%. And the rest of the part had higher concentration, So this means that the lower part with the blue one has a lower potential for hydrocarbon, but the larger part, which had a concentration above the threshold, has higher potential for hydrocarbon. Moving on to the next, the other figure for chromium. You can, the threshold for chromium is 0.009%. When you look at the red part, the concentration is lower than the threshold, and the rest of the part has higher concentration than the threshold. So that also implies that the other part has higher concentration for hydrocarbon, while the red part has lower concentration for hydrocarbons. This figure is for zinc concentration. And zinc concentration, the threshold is 0.009%. And here, the concentration for zinc, the largest part of it had lower concentration compared to the threshold. This could be attributed because zinc is a trace metal which is very sensitive. So because we were using XRF, that could be the reason why. And when you look at the other figure for strontium, you can see that almost all the area had higher concentration than the threshold, which is 0.02%. 0.025%, and that means that there is higher potential of hydrocarbon in that region. For objective 2, which was for TOC, the red line shows the results for the standard, and the blue one is for the sample that we collected. Okay, the results for the sample were below the standard, though we had the TOC, but they were not that rich in source rock. They were still very mature. Conclusion from the results, we've seen that most of the sample were sandstones and shells and limestone, which are very good and potential source rock. And from the results on the TOC analysis displayed, we've seen that they were below the standard, which is 0.5%. Okay, TOC, from the results, okay, TOC is maturity sensitive, therefore is less accurate, and it's recommended that when you are using a TOC, you should use other data in conjunction with it. You can use data from vitrinal reflectance so that you get accurate results. Okay, the study will contribute for future geochemistry, exploration of the zone 1 area. Since we already have the data, anyone can just use it and empower their future results. For business opportunity, private sectors can establish centers which offer geochemical exploration services, equipment use like ICPMS. Also, private sector can offer training on the data and interpretation of the geochemical surfaces results. Thank you.
Thank you very much, Jen Oremo. I think it's a good process that you are taking, mapping on surface. Of course, we use the surface to know what is in the subsurface. If there's indications on the surface, what is down there is a guide. So it's a good reservoir, not a source rock if it has high aluminium. So I've been told to wrap up, but I want to give the audience Q&A, a quick one, so that if you have any question, tell us your name and whom you are addressing to, so that we are able to wrap up. We move to the next session. Help me give a mic to him.
Thank you, moderator. My very first question is, one is to Mboya. Thank you for the presentation. What is the source? What is the perceived source rock and the seal for that the prospects in Ewasi, Wambere? And then for Jen, your model seems to be too smooth. I don't know what's the confidence in what you are presenting, because they seem to be too smooth for us to like perceive the results.
Anyone else? Here in front.
Thank you, moderator, and all the presenters for the wonderful presentations they gave us. I'm going to the
Introduction, please. Name.
Sorry. My name is Simon. I am working for the National Oil and Gas Company of South Sudan called NileBed. I'm the operations manager in E&P. The lady who presented about the melt, sorry, I just forgot your name. You presented to us, you made the studies on the part of the African Valley to see whether there is melt and there may be eruptions, and you concluded that when or if the crust is thin, then there is probability of melt or what we call magma. And also you concluded that there is where in your study area there is there will be no melt or there will be no magma. And I wanted to ask you about considering is it only the thinness of the crust that decide whether a reef system has a melt, or if you consider the water bodies, because the East African reef system is actually, having a number of a number of water bodies. And I don't know if you have considered that factor, that it could also lead to no melt in the thin crust. This is part number one. Number two is just for the purpose of information. There are rumors that the East African reef system is going to divide Africa into two continents. I don't know when, in how many million years, of course, geologically, but these are rumors which have not been confirmed. I don't know whether you have heard about it. If you can shed more light on that, because you are now studying a very complicated phenomenon of plate tectonics. Thank you.
Thank you. The last one, maybe perhaps from our lady. If no, I think the questions have been addressed to all my three presenters. One of them had a flight to catch. Apologies from her, but I think the context is behind it, just in case you need to interact with that. The one on the Pemba trough. So I think I'll welcome. The first question was on EAPCE, so you can respond.
All right, thank you for your question. Basically, as I started explaining about the history of East African development in the part of EAPCE'23 block, it started since Miocene with the first rifting, and this rift triggered some kind of erosions of the clastics, and these are the conglomerates, sandstones, and shells. But shells, we can see the outcrops for the conglomerates and sandstones, but we don't see the shells. And we tried to model in respect to the geological principles that whenever there is erosion and depositions by fluvial system, there is a kind of sorting, and we anticipate that as you move from the flanks of the basin towards the deeper part of the basin is where we anticipate the presence of these shells. We haven't intersected them, and they are not anywhere exposed. So what we are doing is we are planning to perform to acquire 2D seismic data, of which will give us some packages that are within our basin, and from there we can interpret for surely the presence of these source rocks. Then within the same package, that is Miocene package, clastics, there is a good, well-sorted sandstones, and this a potential reservoir. Thank you.
On the question on the level of confidence, okay, we used SAFA9 software and our level of confidence was 95%.
Thank you so much for that good question, Sam. Okay, so let me begin with the last question. You talked about how Africa is dividing. Yes, there is that anticipation, the way we see what happened in Madagascar, because they say that it was once all Africa and then it separated. But currently, one of my other projects that I'm doing is I'm installing GNSS stations, those are GPSs that are reading the rate at which the Albertine or the Northern Western branch, the way it's separating. So I installed the stations in 2021, and for me to get good results, I have to make them read like for 2.5 years. So after 2.5 years, I'll still use them and then try to see at what rate they are moving. But definitely, if something is separating, then at one point in time, probably it will really separate. Like, I don't know how many million years. About the thinness of the crust, does that really mean that there's melt? So when you look at how, like, down when melt is coming, like it's kind of pushing, so that makes it like to be thin, like makes the crust or the lithosphere to be thin, but it's not conclusive. My project, we are a bunch of us like doing different things, so that people are doing MIT, and those are the ones who really conclude whether really, like, we are doing different bunch of things, and then we see if probably at the end of it all we have a conclusive conclusion, whatever. Thank you.
Thank you. Let us appreciate the presenters. So it has come to the end of this session, but I think there is a token for the presenters. So you can come here for a quick photo, and then we are free to move to the next session.
Good afternoon, everyone. Welcome to the new session, the East African Offshore, Coastal and Rift Basins. I know it's a wrong time because we are moving towards lunch, but we are going to try as much as possible to run quickly so that we catch up with the lunch. My name's Dr. Simon Echegu. I'm a lecturer in Makerere University in the Department of Geology and Petroleum Studies. I have a PhD in geology, specializing in petroleum systems analysis and modeling. I'm so passionate about petroleum systems modeling. And I'm also very passionate about training the youth. So going back to the topic of our session, I really want to say that if you're a geologist or if you're a geophysicist, you will be aware that the rifts and the offshore really contribute significant amounts of hydrocarbons. So there is no doubt that even the East African rift and East African offshore will be having that potential. Indeed, if you recall the previous discussions we had from day one, where they're talking about the country presentations, at least it indicated that there is potential in the region. Also, going back to those presentations, you note that the area of East Africa is really underexplored. So it's only prudent that we do more serious work so that we can unleash the potential of East Africa. You'll also remember in the previous discussions that based on the discoveries that we have so far, we have put a lot of infrastructure aiming at really making good use of these resources. So again, it will be important to be able to feed into this infrastructure by really increasing the effort that we are using in exploration so that we can be able to make good use of the infrastructure. And a good thing, we are lucky today because we have within us here 5 people who have done some work in the area, and they will be telling us what they have done in relation to unleashing the petroleum potential of the East African offshore, coastal, and rift basins. We are going to start with have a group of 5 people. But when I was coming, there was one person who was presenting. I think he came from a different lot. So I don't know if there's going to be an exchange. Otherwise, for now, I will be having only 4. So we are going to start straight away with Honorable Dr. Samuel Diariga. Yes, that one. So when you come here, I'll request that you introduce yourself the way you want. I don't want to dilute you. But be aware that you have only a maximum of 10 minutes, including introducing yourself. Thank you so much. Let's welcome Dr. Samuel to the floor.
My name is Honorable Samuel Ndairagije. I am from Burundi. I am a former minister in charge of minings in Burundi. I have also been a senator in the Senate of Burundi. Now I am a professor at the University of Burundi in the Department of Earth Sciences. Okay, what I will tell you is about search for hydrocarbons in Lake Tanganyika in Burundi, current situation. First of all, let me apologize. I made just a short presentation. I was told that I had to make only 7 slides, and I respected. Okay, first of all, there is a short introduction. After that, I will tell you about geotechnical and physiological context in the northern Lake Tanganyika basin. After that, I will tell you about the total organic carbon in that area, and I will finish with a conclusion. Okay, everybody, I think here, you know, where is Burundi? Burundi, a small country at the crossroads with East Africa and Central Africa. Burundi is sometimes called the heart of Africa. Lake Tanganyika is a lake which is on the western border of Burundi. Lake Tanganyika belongs to the set of the East African Great Lakes. It lies, as I say, in the western branch rift of East African rift system with Lake Albert, where billions barrels of oil have been discovered these last decades. That East African rift system is now considered as a modern analog of the Crescentaceous rifts, where many fields of oil have been discovered in Brazil, in Nigeria, in Congo, in Angola. Lake Tanganyika represents biggest interest in oil exploration because it is the deepest and the largest of the western branch. Let's see. This one. Okay, geotechnical or catastrophe. That's a help. Okay, geotechnical and physiographical context of northern Tanganyika Basin. The modern geomorphology of the Rift Basin is divided into two main bathymetric basins. There is a northern and a southern that are separated by a trending ridge called Karemi-Mahari Ridge. Burundi is in the northern bathymetric basin. Northern basin is divided by striking faults into three sub-basins: Bujumbura, Rumonge, and Kigoma sub-basins. The maximum thickness of the sediments field is around 4,000 meters sedimentation. The sedimentation started in the late Miocene or early Pliocene. Let's see this one. Okay, total organic carbon in modern sediments from northern Tanganyika Basin. 400 grab samples and 25 cores were collected during the GeoRift project of EAPCE'23 from 200 to 600 meters water in the Bujumbura, Rumonge, Kigoma sub-basins. The goal for that study was to study the distribution of organic phases. At the right, though, you see the map of that region. You can see in dark color where are the high contents of hydrocarbons. Average of 4.3% and a maximum of 12 total organic carbon have been found in modern sediments of Bujumbura and the Rumonge sub-basins where Burundi is. When they analyzed these samples, they observed many diatoms that appeared as the main component in the sedimentary organic matter. As you see here, there are also some dashed areas that are also rich in total organic carbon. The big area, which is black, is the Cape Kalamba in Congo, where nowadays you can see some sweeps on the surface of the water. The surface of the water. Okay, let's see. Up. Preservation of such quantities of organic matter in the deep basins sediments is explained by anoxic conditions which prevail below about 100 meters over most of the bottom of the lake. Organic sediments may accumulate in the deep axial basin on the lake, forming highly petroliferous sediments. High petroleum potential sediments are forming in close proximity to low petroleum potential sediments. That is a big problem in sampling. In terms of source rock, the Tanganyika sediments appear extremely heterogeneous. In terms of preservation potential, Lake Tanganyika offers optimal conditions. Tectonic settings favorable to reserve formation are axial and lateral littoral platform sediments, large sand bodies, five-grained sand carried by rivers like Malagarasi, like Rusizi. These fine grain sands are carried and transported offshore into deep offshore basins. It is this one. This is a cross-section between Congo and Tanzania, North Tanzania via Burundi. It's a geoseismic section which shows us the main traps. In the green color, you can see the areas that are rich in organic matter. We are in the share as sediments. You see that in the Congolese region, there are a lot of these facies. For Burundi and Tanzania, the main traps of potential traps of oil, potential facies of traps must be some sands. They are in the yellow color. So what you can see, there are potentialities of oil, potentialities, but no oil field have been discovered. You see the circles. The circles shows the potential main reservoirs of oil. Okay. Now I will tell you about some licenses granted to Burundi, and I will give you a short conclusion. Various studies has been conducted since 1959 for petroleum exploration, both in the Rusizi Basin and the Lake Tanganyika. Around 1980, Amoco Production Company developed exploratory work. 2 boreholes were drilled in the Buringa and the Rusizi sector. Here we are in the plain of Rusizi, it is onshore, but no one of these boreholes yielded oil. What they did, it was a shallow drilling. They drilled to 800 meters, where there is a thickness which is around 3,000 meters. In 2008, Burundi's acreage was divided into 4 blocks, A, B, C, and D. Block B and D were awarded to Shellstream Petroleum, while A and C were later awarded to AZ Petroleum Products Limited and Minergie. That period, I was the minister. I signed the convention with Shellstream for blocks C and B. I hoped that they will make a good job and find oil for us. But what they did, it was a compilation of the existing data. I said that unfortunately, these companies did not find oil in Lake Tanganyika. But Lake Tanganyika and the plain of Rusizi keep still of great interest for hydrocarbons exploration. Only 2 boreholes can't make somebody make conclusion. A regional collaboration, especially in the East African community, could offer a best policy contexts and opportunity in the area to open multidisciplinary data exchange, especially in hydrocarbons exploration. Thank you.
Thank you, Dr. Samuel, for that beautiful presentation. Another hand clap for Doctor. At least no discoveries yet, but there is big potential. We have seen beautiful traps and we have seen good source rocks with very good TOC. So it's just a matter of time and there will be a discovery in Burundi. We are doing badly on time. Let me now take this opportunity to call Elizabeth Kimbure. If you do us 7 minutes, we shall be very happy.
Good morning, everyone. Good afternoon, sorry. My name is Elizabeth Kimburi. I work with the National Oil Corporation of Kenya as a geologist. And this afternoon, I'm pleased to present to you a paper that was done together with the Core Lab, which is a UK company, just to understand the reservoir quality of the Miocene carbonate rocks in the Lamu Basin part of Kenya. We'll begin by looking at the location of the Lamu Basin and a brief description of the same. That is the map of Kenya, and the circled area is where we are going to concentrate during this presentation. It refers to the Lamu Basin, and the Lamu Basin is described as, that is a brief. It is located in the southeastern part of Kenya. It is a basin that extends over 256 kilometers, both onshore and offshore. The basin stratigraphy spans from Permo-Triassic to late Neogene epoch. That is basically from Karoo to Pliocene. And the basin is characterized by the extensional tectonic style. And numerous authors have defined it as a failed arm of a triradial radial rift system. And we notice that during Mesozoic age, there was a drift of the Madagascar, which later allowed the Indian Ocean to form. So during this study, where we wanted to study the Miocene sediments, we had three main objectives. One was to review the sediment reservoir descriptions within the basin. The second one was to highlight the factors that controlled the lateral and vertical distribution of Lamu Basin reservoirs. And the third was to look at the potential from paleogeographic maps that illustrate the evolution of the basin while interpreting the complex interaction between sedimentation patterns and the structural architecture that exists in the Lamu Basin. We adopted a methodology which involved the biostratigraphy, which was an age calibration technique, just to understand the paleoenvironment that existed during the Miocene times. We used three elements of biostratigraphy, which included palynology, micropaleontology, and nanofossils. We went to the next step, which involved use of cyclostratigraphic analysis and analyzing the gamma ray log, which clearly detects elements of radioactive, which are the thorium, lithium, and potassium, and uranium, sorry. So those three. And we related the data from cyclostratigraphy to the biostratigraphy data. And we were able to see the successions in our sediments, which revealed cyclic and rhythmic sedimentation successions. Next was to look at the whole cores that were available from legacy data. And with that data, we were able to look at also petrographic analysis of our representative fascies. This was able to give us basic porosity and permeability measurements just by the look of the eye. Then we looked into more detail on petrophysical characterization using a technique known as rock typing. And here we were clearly looking at sample cuttings of uncored intervals in the wells that we had, which are located in our Lamu Basin, which will be observed in the next map. So basically, That is the map which is trying to zero in on the wells that we'll be talking about. There's a Kenkan, there's a Hagaso, there's a Pate, which is on continental shelf, there's Maridadi, there's Simba, which is further deep offshore. And maybe we begin, but what we noticed. Our results showed that the Miocene carbonates are generally noted to be evident in the Lamu Basin, and they have different properties which range from bioclastics and Pake stones and Wake stones, which are basically grain-supported sediments. And these showed variable porosities with permeabilities ranging from poor to moderate. The poropan plot, which is the diagram on your far right of your screen, is basically a permeability against porosity plot. And we can see where our wells plotted. The Maridadi are the ones in red. Then we have the green, which is Dondori and Pate. And you can see where they plotted up there. And then there's the Maridadi well, which is right at the top. So let's look at the analysis. The poropan plots showed that the Hagaso well and Pate well showed good reservoir quality. They plot right at the top there with values which range from about 20 and good permeability. This was in the carbonate shoreline and the shelf sediments. So on our map, we can see where Hagaso is. It's right at the continental carbonate up there, carbonate shelf. And Pate, on the other hand, is right at the margin of our shelf sediments. And we notice the intervals at which Hagaso well had good reservoir properties was about 400 meters, while for Pate, we got two intervals at 700 and 1,000 meters. We went on to look at the Dondori well, which is also important, which is on the right of the Pate well. And we used a technique called helium porosity, which enabled us to get a good to moderate porosity value of about 16.3% at 100 meters, and another interval of which which gave values of 24.7% at over 1,000 meters. And however, with such good porosity values, we noted that the permeability measurements were not very good, and this was because of the metric matrix that is usually one of the inhibitors in carbonate reservoir sediments. The other well that we looked at was the Maridadi 1B and the Kenkan well. And we can see that the Maridadi 1B is a well right onto our carbonate shelf. And this was critical because it gave us relatively good values, which are the red values. We got a couple of samples. And however, we can note that one sample plotted very low permeability and porosity, which is the value right at the bottom. And this was also due to metric matrix, which affected the macro porosity. And then we can go to the next slide. The other result that we wanted to project was using the paleo geography. And this map is one of the most important ones to understand our Lamu Basin trends in terms of how the structures are forming and how the sediment patterns are changing. The main structural element in the Lamu Basin is the Devi Walu and Hagaso trend, which is a dark line which comes from the north to the south of that basin, the blue part. And we can see that it controls sediment patterns in the Miocene Basin from the Kenkan well, which is located slightly north of that trend, and the Walu well, which is a bit south of that trend. And this trend enabled us to notice that those are western progression of the carbonate shelf towards the west in our map of Kenya, and then an incursion of proximal clastics towards the east. So the Devi Walu Ridge has been noted to have divided the Lamu Basin into two, where we have one side of the basin is clastic ridge, and the eastern side is, the western side is carbonate rich, and the eastern side is clastic rich. Maridadi 1B also gave us good values in terms of understanding how the sediment patterns were coming in during the Miocene. We can see it plots just right off the carbonate shelf. It's one of the grayed areas in that little picture. And what happened is, for the Maridadi 1B, we noticed we had got very good limestone fasces. And with the limestone fasces, we also noted an incursion of sandstones and shales, which is indicated by the yellow color just right at the edge there. And that one suggested to us that there was a delta that was bringing in sediment rich in clastics and shales. And therefore, you can see the dominance started coming through towards the end of the Miocene. The other well that we looked at, which was critical to understand how the carbonates were developing in this basin, was the Simba 1, which is it's a deeper offshore well. And in that well, we noticed that the lower Miocene sediments are missing. And this was okay, which we understood this to be occasioned by an uplift during that time. And the structural trend then moved our sands that were coming into the basin through an axial intervention. They moved axially through into the Tanner syncline and other topographic lows that existed between the structural trends that are in the Lamu Basin. What I would like to conclude is, to conclude my presentation is to say that we notice the carbonate facies tend to have numerous variations in terms of, next slide, please. The carbonate facies range from, give different ranges in terms of how the pore types vary from vaggy to moldic to fractural. You can read that for yourself. And also the range in terms of porosity varies from very poor to very good. So what we can understand by this is that when you're handling carbonates, do not just look at the lateral one well and assume that the whole expansion on a certain scale will give you the same porosity and permeability values. You need to look at small intervals because carbonate buildups range in terms, depending on what climate was available and of course the structural elements. And finally, what we would want to say is that we have seen that the shelf edge carbonates present better reservoir qualities in terms of the values that we have seen. And these are, you can compare those with the onshore and offshore blocks, onshore and offshore zones, which do not give such quality reservoir properties in terms of the carbonates. And also, in terms of sustainability and economic prospects, we would want to welcome any investors who would want to look into the reef carbonates of the Lamu Basin because they show potential in terms of hydrocarbons. And this can be, we can give one example, sorry, let me just close, where the Sandbad well, which was drilled in 2014, we were able to get good porosities in the dolomites that were found in the Sandbad well. And they also got gas shows. So, and these carbonates were also of Miocene age. So it's something that we need to look at as potential investors so that we can open up this Lamu Basin for other prospective elements of the hydrocarbons and gases that might be available in this basin of ours. Thank you very much.
Thank you, Elizabeth, for telling us about the porosity and permeability of carbonates in Lamu and for inviting the investors to go to Lamu. We are running out of time. Quickly, let me go to the next speaker, Mr. Ndubusa. Mr. Ndubusa, you're welcome. Mr. Ndubusa, let's try to keep time. 7 minutes again.
Thank you. My name is Tryphon Dubusa. I work as a geophysicist at the Petroleum Upstream Regulatory Authority. And I'm going to take you through, I'm going to take you through summary of the results of the recent field study at the Rukwa Rift Basin. A quick introduction, the Rukwa Rift Basin is one of the world-class Phanerozoic rift field sequence found in the southwestern Tanzania along the eastern branch of the East African Rift System. The basin encompasses a sedimentary thickness of approximately 12 kilometers and is also potential for hydrocarbon and helium explorations. Next slide, please. The objective of our study is to analyze the subsurface geology of the Rukwa Rift Basin, so as we can see if we can come up with some information that can add to previous exploration in the basin and also add future hydrocarbon exploration in the Rukwa Rift Basin. And the methodology that was used is the assessment of hydrocarbon system elements and hydrocarbon shows and the general subsurface geology of the Rukwa Rift Basin using drilling data. The major drilling data that was available and used with the drilling cuttings and the summary of the results of the cuttings will be summarized in the following sections. We also made some field visits around the areas which had different hydrocarbon signatures so that we can observe and add more information to our study. Next slide, please. Okay, the results of the logging of the cuttings were summarized by using the constructed stratigraphic section of the Rukwa Rift Basin and with the aid of the geological prognosis that was provided by the drilling contractors. And through our analysis, we observed three formations, as you can see in the constructed stratigraphic section of the well A. The first formation is lake beds formation, which are characterized by a thick sequence of sands and also some claystones, which had some minor bioturbations. Also, the second formation that was observed was the red sandstone. The red sandstone is characterized by the thick sequence of sand and very small amount of claystone, approximately 10%. And the lowermost formation was the Karoo formation, whose upper part was made up of 90% of shells, which could infer the presence of an active seal in this formation. And the lower part was mainly made up of sandstone. But the evaluation of the lower part was difficult due to some drilling challenges at depth. But there are some guest shows which were observed during drilling in this formation. Also, we could also infer the source rock potential of the Karoo rocks due to heating effect of the pluming activity that is underneath the East African Rift system could have heated the Karoo rocks large enough so as could act as source kitchen to the observed hydrocarbon gases that we are seen seeping in different areas around the basin. But we are not disregarding the contribution of source rock in the lake bed sequence. The results of the cutting logging were also supplemented by evaluating the geological chance of success in each of the formations. And the evaluation as an assignment of values was based on a subjective analysis evaluation of presence of each of the individual elements of petroleum system in each of the three formations. The three formations have shown the good values, chance of success, but in the lake bed sequence seem to be higher compared to the other two formations. So if we are to drill in the basin, the major target should be in the lake bed sequence. And the figure on the right indicates the schematic section of the Rukwa Rift Basin as it can be seen in the interpreted 2D seismic reflection line. Different observations were also made in the field. Major gas were seen to be bubbling in different areas, especially on top of hot muddy water surfaces, and also in flanks of the salt evaporation ponds. Gases were seen to be bubbling in these areas, both location and the vicinity of Lake Rukwa, just a few kilometers southeast of the Lake Rukwa. So having all this information, what is the way forward? We can infer that the Rukwa Rift Basin is potential for hydrocarbon explorations. Having such information, and we would like to welcome investors, researchers to conduct more study in the Rukwa Rift Basin and collect more data so that we can comprehensively infer the subsurface geology and hydrocarbon system of the Rukwa Rift Basin, since it's much more potential and it is analogous to the Albert Basin in Uganda, which has already had a hydrocarbon discovery, and also it's an open block for acreage. So, having said that, I want to thank you for listening.
Thank you, Mr. Ndubusa. Again, no discoveries but all the petroleum system elements exist. So that means that anytime they will make a discovery also. So our next speaker is Petro Theonest. Petro Theonest, you are welcome to the stage. Introduce yourself the way you want people to know you.
Okay, thank you. Good afternoon. Yeah, my name is Petro Theonest. I'm a geophysicist working with TPDC, which is National Oil Company of Tanzania. So this afternoon, I will present to you porosity prediction using post-stack seismic inversion for Block 3 offshore Tanzania. So I will start with project location, motivation, and objective of the study. So the location of the study is under Mafia Deep Basin. This basin accommodates most of the gas discoveries in Tanzania. So the water range is from 200 meters to 3 kilometers. Currently, the block has gas discovery. Initially was under BG, but currently now is open. Before this start, the porosity information was just only known at the well location. So motivation of this start is just to estimate porosity on the entire block. And my objective first is to stratigraphy interpretation, so identify the major stratigraphy. Then to do the seismic well tie, because seismic is in time and well is in depth. So in order to correlate the major events in these two data sets, we need to create a time-depth relationship. And the third objective is to generate a simple low-frequency model. Then to invert the seismic data. Inversion means transforming the seismic data into local properties. And the last one is to use the impedance that generated from the inversion, porosity log, and attribute in predicting porosity away from the well. So the data set and the methodology that used in this study, the major data that used is seismic data, which is the 3D, well logs, which are P-wave, dense, check shots, and the horizon that were interpreted from the seismic data. Then the wavelet, initially I used the statistical wavelets. Then the well tie I improved through extracting the wavelet from both seismic data and well data. So the geological model was generated from the horizon and well data. Then I used the geological model, wavelet, seismic data to do the inversion. Then the output from the inversion is the P impedance. Since P impedance and porosity both are petrophysical information, it means that a linear relationship can be established at a well location, then improved and used to predict porosity on the entire block. So the methodology first is to pick the horizon by tracing them on the seismic cube. Then to do the well tie, initially I used the zero phase wavelet. Then I extracted it from the well and seismic. Then I generated the low frequency model as an initial model because once I generated the power spectrum of the seismic data, I observed that the frequency content of the seismic data ranged from 10 to 70 hertz. It means that 0 to 10 hertz was missing. So the main purpose of this low frequency mode is just to complement the low information which are missing from the seismic data. Then I did error analysis. For seismic inversion, like other inversion, they have a non-uniqueness solution. So in order to have a reliable information, I try to optimize parameter through error analysis. Then from there, I generated the porosity by using the inversion results. Now this is the inversion result. Can you go back, please? This is the inversion results. From the left, that's are the well tops. Then the impedance. The impedance there are three impedances. The blue color indicates the impedance from the log, and we have the light blue, which is the initial impedance. So what I'm trying to do here is try to converge or try to compare between the two impedances. The impedance from the well, which is in blue, and the impedance, which is the initial model, which is in light blue. And in red is the impedance which I'm trying to achieve. And the result was assessed by taking the impedance, which is in red, by convolving with the wavelet, which is in blue. Once you convolve the two, you get the synthetic trace, which is in lead. Then from there, I subtracted between the synthetic trace and the seismic trace, which are in blue, to see if the error is minimum. So after doing so, unfortunately, we cannot see there properly. The difference between the synthetic trace and the seismic trace is 0.07. So after obtaining the minimum error, which is within the threshold, then it means that parameters can be used now, can be applied on the entire block. Because initially, what I did here is just at the well location. So after optimizing the parameter, then I established the relationship between the P impedance and the porosity local, because both are petrophysical information. Then that relationship was applied on the entire study area. Now this is the result. This is the porosity volume on the entire study area. And you can see that the results is ranging from 2 to 25%, the porosity. Now, conclusion, the model-based inversion utilized to invert the seismic and the spatial porosity estimated ranges from 2 to 25. Recommendation, since I used only one, so in the future, maybe more study can be done by including more wells. Also, since I used the post-stack data, in the future, maybe plus stack analysis can be done to identify or to study the elastic impedance. And the government policy of the Tanzania is to ensure security of energy and energy supply. In the future, in case this case is developed, it means that it will ensure energy supply, and also it will inflate the economic of the nation, and it will ensure environmental and healthy sustainability. Thank you.
Thank you so much, Petro, for that presentation. You can see how we could be able to go from seismic data to be able to get porosity. That has been interesting and good. I do not know According to my list, we should be done. All the presenters have made presentations, but there was the last presentation where we had a kind of swap. One person presented. I don't know if the person who did not present is he or she around. She could be able to present in this session. Otherwise, I'm going to take this opportunity now to give the audience chance to ask at least 3 questions. 1 question per person, I think, so that we can go for lunch. Microphone here. Whenever possible, please try to direct a question to the person who made the presentation.
Yes, thank you so much, the moderator. My question goes to Professor Samuel. Thank you for the talk. You said that 2 boreholes were drilled and they were all dry, but it looks like you have this great confidence that there is hydrocarbon there. So my question is, which resource is that? Is it like gas or oil? Thank you.
Another question?
My name is Joanne Nakajigo. To the last presenter, you've showed us how we get the porosity and all of that, and you used the model-based inversion. So why not other methods? Thank you.
The last question. Last question from a gentleman. Yes, right here.
Thank you so much.
Go ahead. Go ahead.
My name is Derek Kimbenyi, and I have 2 questions to the last presenter. I want to know which tools you used, or which software you used for the inversion, and then when you make your model-based inversion, was it forward inversion or you use a different inversion? Thank you.
The last one.
Thank you. My name is Venance. My question goes to Burundi. He presented about the borehole, the wells that were drilled within the Lake Tanganyika. I would like to know, because I know this lake is very deep, from which locations they managed to drill.
Okay, thank you. Dr. Samuel, you have 2 questions. Maybe you start to answer them.
Thank you for the questions. I will begin with Madam. 2 holes were drilled onshore. It was in the plain of Rusizi. Rusizi is a river, a big river. They are looking for both of oil and gas. What they did was to try to get something. Oil and gas. Okay? On a pile of thickness, let's see, 3,000 kilometers. They drilled only 800 meters. It's shallow, it's not deep. I think there is a possibility again to drill in that area. And asked me, the bore they sampled in Lake Tanganyika. There also, it was in shallow water. The deep they collected the samples was 600 meters. Some areas in Lake Tanganyika, the deepest part of Lake Tanganyika goes to 1,400 meters. It was also, I can say, shallow, shallow depth. If I compare what they did with the depth of Lake Tanganyika. The problem is that, or what have been done, they used less means. If there is a such company which can use a lot of money, probably we can get good results, more results than what they got. Thank you.
Thank you. Petro, you had, I think, 3 questions. Petro, come forward.
Thank you. Okay, thank you. The first question he asked me that why I decided to use model-based inversion. The reason is that time was limited because this was through my study when I was doing my master's. That's why I decided to use model inversion. And also another limitation was the software that I used. I used the Hamson-Lewis software. But the second question was which software I used. The software that I used, I think I've mentioned, is Hamson-Lewis software. And another question, he asked if I used forward or inverse. I don't know if I got it correct. I used the inverse. It's called GARI, General Linear Inversion. Thank you.
Oh, thank you very much, presenters, and thank you very much, the audience, for persevering to be here when lunch was just around the corner. Thank you so much. I think the presentations have been very good. At least we are able to see that within the East African area, especially the rift basins that they have presented and also the offshore, there is actually some hydrocarbon potential waiting to be tapped. So we just need to put more little effort in exploration, and we shall be having our oil or gas. Thank you so much. I think we should clap for ourselves for persevering. Thank you. I forgot to mention one person who was helping me somewhere. She's called Nafula. Can you stand up for people to know you? Nafula has been rapporteuring. Thank you. Do we have MC? The presenters, can you move forward? Presenters, please move forward.
surprised, I must say, 'cause I never had seen such a pretty face with such a warm and beautiful smile. It wasn't hard for me to notice her style. I was fascinated, surely. She took my heart and held it for me. I wouldn't let her get away, not until she heard me say, "Excuse me, miss, what's your name? Where are you from? Can I come and possibly can I take you out tonight to a movie, to a park? I'll have you home before we start. you strong. You see me sighing from a view. I can feel inside of you. In a moment, seconds couldn't pass. Let's make this movie journeys everlasting. Let go. Let go. Honey, let go. Let your heart follow time. Let your love follow mine. Let go. Darling, let go. Let go. Let your heart follow time. Let your love